Welcome. This video corresponds to section 1.2 in the Brown SL Chemistry book. And in section 1.2, the first part of section 1.2 starts talking about the mole. And hopefully you remember from previous chemistry classes that atoms are way too small to count or weigh individually. So instead, we use a quantity that's large enough for us to actually measure specifically the mass typically of. And Avogadro realized this amount is going to be a huge number. But he also realized that atoms of any element have a consistent mass based on the number of protons and neutrons, or what are referred to as the nucleons, of the element it contains. So the relative mass of different elements, or the ratio of their masses, should remain the same if you compare equal numbers of each element. For example, if we think about hydrogen, which has, let me just get my pen here, hydrogen, which has molar mass of 1.01 gram, or we'll just round that off to 1, and oxygen, which has a molar mass of 16 grams, that ratio is 16 to 1 oxygen to hydrogen. So what if I had 2 hydrogen and 2 oxygen? Well, now I'd have 32 grams to 2, which is still 16 to 1. What if I had 100 grams of each? Well, then I'd have 1,600 grams of oxygen and 100 grams of hydrogen, and it's still 16 to 1. This is what Avogadro realized, is that the relative mass or ratio is going to remain the same. So with that in mind, he came up with the mole as being an amount. And he said it's going to have to be a huge amount, so it's enough of any element, even little tiny hydrogen and helium, for us to actually work with and be able to weigh. So he came up with a number that's commonly rounded off to 6.02 times 10 to the 23rd. And that's the number of particles in a mole of anything. And the mole is often referred to as the chemist's dozen, just to remind you that just like a dozen is 12 of anything, a mole is this number of anything, whether it's atoms and molecules you're counting, or if you want to count something like jelly beans or pennies. But if you count something like a penny or marbles or jelly beans, it is a ginormous number, and your book gives some references to just how huge this is. You know, marbles would be covering the earth to a depth of 50 kilometers. You know, if it was that many pennies, everybody would be a quadrillionaire or some ridiculous thing. But when we're talking about atoms, a mole of water is only about 2 tablespoons. So a really huge number to count really tiny things. That's what the mole is all about. So a couple other terms that come up when we're talking about moles is this idea of relative atomic mass. And atomic mass is just what it sounds like. It's the mass of an atom. Relative means compared to something. Well, all elements contain what we call isotopes, slightly heavier or lighter atoms because they have a different number of neutrons in them. So just like, you know, some people are heavier or lighter than others, but we have the same basic parts in us. So a sample of any element will contain some of these isotopes, and all elements have at least 2 isotopes or 2 versions. So the periodic table actually shows us the mass of one atom of an element as a weighted average, or called the relative atomic mass. So if you had 100 of those atoms, you might have just a few of this isotope, just a few of that isotope, and a whole bunch of this isotope. So what's the weighted average out of a sample of 100? Relative atomic mass, you might have noticed on my previous slide, is abbreviated A sub r, but it needs a reference point, okay? Relative means compared to something, and such a small amount, isotope carbon-12 is the standard of the reference point. So carbon-12 is pretty plentiful. There is some carbon-14 out there, but it breaks down relatively quickly in terms of atoms. And so carbon-12 is plentiful, it makes up most of the carbon out there. And it's assigned a mass of 12, exactly 12, not 0.001 or anything else. So that's the unit given for atomic mass. Sometimes we call these units atomic mass units, but really there's no unit assigned because atomic mass units are basically a made-up unit. So the relative atomic mass for any atom is the weighted average of that atom divided by 1/12 of the mass for carbon-12. Well, think about it. What's 1/12 of the mass for carbon-12? That's just 1. So it's the weighted average of that atom divided by 1. So we also have what's known as relative formula mass. The relative formula mass would be the mass of just one formula unit or one molecule. So this is referring to a compound, but now we're talking about the mass of just one formula unit or one molecule of it instead of the whole molar mass. So it's determined by adding the relative atomic mass of all the atoms in the compound. And again, no units are needed, or you could use this AMU if you'd like having units on things. So molar mass then is the relative atomic mass of 1 mole of a substance, either an element or a compound, so an atom or a molecule. And this is known as your molar mass, capital M. And now there is a unit. It's grams per mole, or IB likes to write things with using the -1 to mean per mole, whichever way you like it, just so you recognize IB's way of notating it. So now when we look at Avogadro's number more precisely, it's 6.022141129 times 10 to the 23rd, because he figured out the exact number of atoms needed for your atomic mass and your molar mass to be the same value. So if you look at a periodic table, depending upon how many digits it carries out, you'll see that 1.008 is the atomic mass. So 1.008 units per hydrogen atom, and it's also 1.008 grams per mole of hydrogen. That's pretty slick because it saves us an extra calculation every time we look at the periodic table. We don't constantly have to convert between how much does an atom weigh compared to how much does a mole weigh. They weigh exactly the same. The difference is the unit. And that's why some people like to think of this as AMUs, or atomic mass units, compared to grams. So converting between particles, moles, and mass. We don't actually convert to particles that often unless you're talking about something like water quality or sometimes, food standards. Then parts per million, parts per billion can be important. But usually we're converting between moles and grams. So this little graphic just reminds you that to convert between moles and either atoms or molecules, you have to use Avogadro's number, because remember, 1 mole of anything equals 6.02 times 10 to the 23rd particles or whatever you have. So you can either set up a conversion factor with 1 mole on top and Avogadro's number on the bottom, meaning you're going to divide by Avogadro's number, or you can set it up with Avogadro's number on top and the moles on the bottom, meaning you're going to multiply by it. And then we can do the same thing to get between moles and grams. We can either multiply or divide by the atomic mass or the molar mass. And it's simply a matter of looking at your units and making them cancel out to decide if you're going to multiply or divide.